Hello, I'm Joseph Outten, and this summer I worked on protein sequence annotation using convolutional neural networks. Okay, so just some quick background. I'm part of a team with Drs. Andrew Warren and Steve Eubank that is contracted out by FundyCat. They contracted out a handful of teams for this. Contracted out by ARPA, which is the information version of DARPA, essentially, on a project called FundyCat, which stands for the Functional Genomic and Computational Assessment of Threat, which is basically a project that's trying to translate DNA sequences to a potential threat level for a variety of applications. And so one of the ways to do this is by annotating the proteins with essentially what are called domains, which are functional units of these proteins. PFAM is a database that characterizes over 17,000 of these domains, and is kind of what we were using to kind of be like a benchmark data set for this. And the state of the art for this kind of annotation process is called InterProScan, which takes in all these thousands of hidden markup models, as well as consorts some other tools and databases to make predictions on annotation. And so we're trying to use convolutional neural networks to see how that changes prediction and increase efficiency and potentially accuracy of that process. So some background on the data. So we're working with amino acid protein sequences, and they come in kind of two forms that are relevant to the project. The first one is core sequences, which are essentially the domain sequence with very little noise flanking either end, and profile sequences, which have a high amount of noise on either end of the domain and between domains if there are multiple domains in like a query sequence. And so Hammer is a tool that we were using to emit training data essentially from the hidden markup models from the PFAM database. Its kind of architecture is shown at the top and its logo is shown at the bottom. Essentially he uses these hidden markup models and emits example amino acid sequences for those domains. So my first order of business for the summer was just develop a wrapper to automate this training data generation. And so I'm just putting in the name of the domain that I want to get out, and it'll give me any number of examples in the core profile setting. Okay, and so some previous work that's been done in this project, some previous undergraduates as well as a current postdoc, Dr. Jacob Porter, we're working on this convolutional neural network. The architecture that they came up with is on the right-hand side. And it shows pretty good core performance, which is like predicting and annotating on core sequences. However, it showed pretty or poor performance on profile sequences, and that's a problem we're trying to deal with. As well as it can't hold all the domains without suffering some accuracy and F1 score. So we're trying to figure out how to deal with that. And so one of the first things they did for the summer was look at a recent Google research paper, which published on this topic. They had one convolutional neural network that basically was predicting on all these domains. However, we quickly figured out that it also had the same problem with not being trained on and predicting on profile sequences. And so that necessitated a model that would be able to only require the CNNs to predict on core or core-like sequences, was able to consult a number of CNNs because we can't put all the domains in one, as well as be able to annotate multi-domain sequences. And so that's where my work came in, the primary amount of my work. The solution for my project was to basically build a sliding window wrapper for CNNs with similar length domains. And so the process for this tool is shown on the top right here. And so we sorted all the domains by length and then took 100 length bins, this is just our first iteration, 100 length bins of these domains and trained a CNN on all of these bins. So we have like a set of CNNs to cover all of the 17,000 domains that we're working with. Basically we take a query sequence and we will break it up into subsequences that are appropriate for the domain length for each convolutional neural network. And that makes it so that it's only predicting on core-like sequences. And so after breaking up and making those CNNs predict on all those subsequences, we get an array of most likely domains from each subsequence from each convolutional neural network, and use a greedy algorithm to take the highest probability non-overlapping domains from that output. And that's essentially the annotation that we are trying to generate. So the bottom left-hand side of this slide shows the histogram of the PFAM domain length. You can see there's pretty high kurtosis. So that shows that most of the domain bins are going to have similar length domains, except for there's some skewness on the right. So that might show some problems for the accuracy of like the bigger length domain convolutional neural networks. we have to figure out how to work around that. And then the heat map on the right-hand side, just a visualization of the confidence for each model for each subsequence. And so the models have different lengths that are associated with the domain, which is why there's a bigger like white region. Essentially, that's the section that it's not predicting on anymore because there's not enough left for the sequence to make a subsequence. And the greedy algorithm just takes the darkest one of these sections and then just nullifies anything that's overlapping with, and then continues that until it has a complete annotation. And so current results show that even though all these CNNs have a pretty high F1 score and accuracy on the domains that they were trained on, there is a high rate of false positives within this wrapper. And we are seeing that a lot of that is being caused because these CNNs are overly confident about predicting that one of their responsible domains is in a subsequence that is not contained in. And so we're trying to figure out why this is happening, and some potential causes are that it may, well, basically some solutions that we're trying to show are that adding an adjunct class, basically, so that if we have these CNNs, we can also train them on some subset of examples from all of the other domains, so that each CNN can kind of decide whether or not a subsequence is something that it should be responsible for, as well as we're seeing some of this, some of this high false positive is caused by similar length CNNs trying to predict on domains from each other's responsibility. And so we're going to try to do some overlapping in the responsibility, basically which domains each CNN is responsible for, to try to mitigate that cause. So other than that, we're also going to look into improving efficiency using GPU and multiprocessing, as well as improving the interface as a tool for future work. And that's what I'll be working on in the next couple months. So that's my project.